When we were looking at the fertility and life expectancy data, we noticed that larger X values, larger fertility rates, are corresponded with lower life expectancies. So that led us to talking about a negative linear relationship, and that leads us to other types of relationships. So there are positive relationships and negative relationships. Positive are also known as direct relationships, and negative are inverse relationships. Now, what does this mean? Well, direct relationships means when x goes up, y goes up, and when x goes down, y goes down. There, I used some arrows to try to make that clear. So as x goes up, y goes up. As x goes down, y goes down. They go together like peas and carrots. So for a negative linear relationship, it's the opposite. So as x goes up, y goes down. And as x goes down, y goes up. So we already saw an example of negative linear relationship, namely fertility rate and life expectancy. So we saw that as the fertility rate went up, the life expectancy went down. So what's something else that could affect life expectancy, but in a different way? So in a more positive way, we have to think of something that we could increase, and as we increase it, life expectancy increases. So if we increase how much money we spend on healthcare in a country, for example, well, I would imagine that the life expectancy will also increase. Now, is it a lockstep relationship? If you spend money on healthcare in a country, will it automatically mean your life expectancy goes higher? The answer to that is no. This is an algebra class. This is statistics. So the answer is maybe. Depends on where you spend it. Depends on how you spend it, etc. But nevertheless, you can imagine that's an x variable that might have a positive relationship on life expectancy being the y, and fertility rate would have a negative relationship because as fertility rate gets higher, life expectancy is actually lower because countries that have a high fertility rate tend to be poorer countries that don't spend a lot, for example, on infrastructure or healthcare. Now, there are other relationships, but they're not as important to us. They're actually nonlinear relationships, relationships that are very interesting to study, but they're not something we're going to study in this class. There's the quadratic relationship that forms kind of a parabola shape, and there's an exponential relationship that forms a curve. Exponential in particular is very important for like population growth and stuff like that. But we're not really going to look at those other than to say, yep, those are there, but we're not looking at them. The one that we are going to look at sometimes is a relationship that has no correlation whatever. It looks like somebody just threw the points out there into the sky, so they have no pattern. So for example, the classic example is height and IQ, right? Somebody's height, if it's an adult, their height and their IQ should have no bearing on each other, despite what the very old-timey song saying short people have got no reason would say. Height and IQ, if I could spell, and IQ have no relationship to each other. Something to keep in mind is that this last graph has no relationship whatsoever. Nonlinear patterns, these ones in the middle, they have relationships. They're just not relationships we're going to study in a Statistics 1 course. So just kind of keep that in mind. They are studied, they are important, but they're not something we're going to look at. We're just going to look for lines in our class. Speaking of which, we need a way to kind of gauge things about those lines. So we're going to look for linear patterns, so correlations that are linear. In particular, we're interested in the strength and direction. So direction is it going positive or negative? And the strength, how strong is it? Now the perfect relationship is very strong. The best you can get is perfect. And then strong is next good. That's a word, next good. And then moderate, and then weak. And weak is terrible. Or no relation whatsoever. So we kind of want to look over these graphs and figure out which one we think is perfect, which ones we think are strong, moderate, weak, etc. Well, the perfect ones are really easy to spot because the perfect ones is like algebra class, which is these top two graphs here on the top left and top right. They are perfect. They are what algebra does, right? Algebra will get you your y equals mx plus b and everything follows like ducks in a row. That's a perfect relationship. We don't work with perfect relationships very often, but there you have it. All right, so rather obviously this one on the left is a perfect negative and this one on the right is a perfect positive. Matter of fact, I'm going to go with positive will be green and, or I'll do blue. Positive will be blue and then negative will be red. There we go. Now we can really tell them apart. Okay, so now what about these other four? Well, this one on the left in the middle, so the middle left, is rather obviously negative. It's not perfect, but it's quite strong. Believe it or not, that's actually what a strong relationship looks like. You can very clearly see the trend line in the middle of that graph. So that's a sign, sorry, this graph right here, the one on the left. So that's a sign that that's very, very strong. And the one on the right is moderate, maybe strong. It's a little hard to judge, and we're going to talk about that in just a second. But that's exactly the conundrum I want you to be in, the kind of confusion of like, is that moderate? Is that strong? I would say it's probably moderate. Well, actually, I'd say it's strong. Look at it. But it's kind of a judgment call at this point. So hold tight. So we've got to come up with a better way to judge that. And then these two, well, this one on the right is weak and positive, and the one on the left is no relation at all, because that just looks like somebody just threw the points up there. So the one on the left is no relation. The one on the right, weak. I mean, it's a little bit, bottom left corner to top right corner, but it's not very clear. So we really don't like this one right here. So it's one to pay attention to. This whole like, how do you know if it's moderate? How do you know if it's strong? That kind of is yucky. Mathematicians don't like having to make a guessing game about something like this. They want to have a number that's going to measure it for us. So I want to focus on this one right here. So this one we don't like. We want to kind of pay attention, right? This is just making guesses is no way to make a judgment here. We need a way to measure it with a number. We need a number that will gain strength. I'll just say we'll leave a number. We need a number. And that number is what the correlation coefficient is going to do for us. It's not going to leave us hanging with this whole like, I don't know, is it moderate? Is it strong? It's going to say, yep, you'll be able to tell whether it's moderate or strong based on a numerical value.